Hello, good afternoon. Here's Lynn from Unity. I'm going to share with you our latest developments in using graph-based technologies in fraud detection. First, let's talk about Unity. Unity is a video game software development company. We provide game developers with real-time 3D development platform. Moreover, we also help game developers monetize their games by selling in-game ad placements to advertisers. So the mobile game industry is one of the highest performing industry globally, with more than 85 billion US dollar in revenue for 2021 and more than 18% overall compound annual growth rate. The majority of game revenues will be from mobile by 2023. And for Unity, in Q4 2020, Unity ads reported 23 billion plus ads served each month. The average time players spend on Unity mobile games is 2 hours and 22 minutes per week. And more 50% of all new mobile games are powered by Unity. So it's a prosperity industry nowadays. So before I introduce our graph-based work, we have to first talk about how does game advertising work. In the world of game advertising, there is a supply side, the game publishers, and there is a demand side, the advertisers. Unity ads connect them by holding a unified auction. From the supply side, the source games who sell their ad placements will send ad requests to Unity ads. And then the advertisers from the demand side will bid for these placements to show their ads. The winning bid will be able to deliver their ad creatives to ad placements and trigger ad events, notably ad events. We will talk in detail about this later. Then when certain ad events are triggered, the advertisers will pay $1 to the publishers. Then basically that's how the game ad developers make money in the world of game advertising. Now, what's the problem? There's a problem we have to talk about. In the real world, not every publisher is honest in game advertising. Some of them, we call them fraudsters because they're committing fraud in this system. A fraud is a malicious activity aimed to generate unearned benefits. And most of the fraud are committed by publishers, and that is my domain. I'm from the department which detects the fraud. And our goal is to protect our advertisers from invalid activities and ensure that our advertisers are confident in our network. Now here comes the definition of fraud. What is fraud actually? With fraud, there are many types of them. So according to Unity's policy, there are a bunch of fraud, endless of them, and we're seeing new types emerging every day. So it's really an annoying problem. According to our experience, there are a few common types of fraud. One of them was the device farm, and also SDK spoofing, click spams, bots, incentive abuses, and others. So they're all very common type of fraud in the world of game advertising. And that's why we need graph-based technologies. So before we have graphs, how do we detect fraud? As I just mentioned before, we have ad events, right? So, and those ad events, they happen in games during advertising. And they does not come along. They come in a cluster. They come sequentially, which forms the ad events patterns. We can see their pattern 1, pattern 2, pattern 3, pattern 4. There are many different combinations and many different shapes of their patterns. That's how we're dealing with the fraud nowadays. We collect and analyze those ad events to find potential fraudulent patterns. And we also aggregate different kind of ad events per different entities. For example, we know there are publishers, there are games, there are users, and join those aggregated results with entity features and their embeddings, we got it elsewhere. Let's see. So here's an example what we're doing. And as you can see in this picture, we have multiple pipelines, one for publisher, one for game, and one for users. They're completely independent with each other, except that they use the same source ad events. And then we aggregate those ad events and concatenate them with different kind of features from different aggregation level. For example, there are publisher features, there are publisher embeddings. We concatenate them with the publisher level event aggregation. The whole feature vector would go through our machine learning based pipeline. And then there are different kinds of models assembled together to make predictions at each aggregation level. So after the run of these three pipelines, we would have three different kinds of predictions, one in publisher level, one in game level, and one in user level. That's how we detect fraud without using graph. Now here's a problem. Now what's the problem? The problem is these results, they're not necessarily agree with each other. I mean, always. Then the problem is that I don't think they're really independent from each other. For example, if we predict a publisher to be fraudulent, is that possible that all games under that publisher are innocent? That's very unlikely to happen in the real world. So in the real world, we have an entangled web we weave. So everything is connected together in a real game advertising network. For example, in the picture, we can see that there are many games under one publisher, and there are many users playing a game. Moreover, one user, for example, user 3 here, the user can also play another game, say game 3. And user 2 and user 3, they can share the same IP address, or their IP can be very close, which is very likely to happen in the same device farm or in the same VPN address. And that's the real world problem we are facing. We can see many fraudulent patterns from those connections. And that's how the initial idea or motivation we're trying to use use graph to solve the fraudulent problems. So what is important in this graph? One of them is the neighborhood topology. We can see that the games, publishers, and users, they are connected with each other. They're forming communities and clusters. And there are many shared information between two entities as well. So let's move on and see what is the approaches we're using. One of the approaches we're using to perform graph-based fraud detection is that we are doing fraud information propagation. For example, as I just mentioned, we have multiple independent pipelines for predictions at different aggregation level. And now, how do we combine those information and give a comprehensive view of the fraudulent possibility of each entity? One way is to pass and aggregate the node features and their individual predictions via message passing algorithms. For example, as a label propagation. This is one of the most well-combed algorithm, and it's also very simple. So we aggregate the information from the neighbors and then use those information to update the central node, to update its predictions, and also it's possible to update its features. Then after the adjustment or the message passing phase is done, we could get a comprehensive view of each entity, and then we would use this entity for the following business operations. Then we also would add this in our report to our customers, so that is more convincing and is giving a comprehensive view to it. Another approach we're using is fraud community detection. As we can see from the graph, fraud games and non-fraud games, usually they do not come alone. They come in a cluster or they come in a community. The fraud games are tend to connected with fraud games. and non-fraud games tend to be connected with non-fraud games. There are exceptions as well, where we can see in the central cluster, we can see the community of non-fraud games are connected with the single fraud games, which is mixed in the innocent community. This is hard to detect. What is easy to detect is that we could find those isolated orphan nodes of non-fraud entity and fraud entity, and also a small cluster or a small community of fraudulent games. That's what we're doing. It's fraud community detection, in which we're trying to find the fraudulent entity groups via community detection algorithms, like Louvain algorithm and some other things. Here we cannot provide too much details because the fraudsters, they're very clever, and they might use those information to reverse engineer our techniques. So here's just some high-level summary and overview of it. Okay, and besides these techniques, we're also trying to use graph-based approaches to generate node embeddings in the game advertising network. As we can see, there are many ways to create embeddings. Previously, we're using non-graph-based approaches until we realized that everything in this game advertising network are connected with each other. So using graph-based embedding approaches would be able to create the embeddings containing the neighborhood topology information of an entity, especially in some specific problems like the target game spending profiling. For example, we can see that in the ads network, the publishers would have their source game, and the advertisers, they have their target game, which means they want their targeting games to show ads in the source games. Whenever a user click the source game and click their ads, then their target game will be promoted to the users. Then the advertisers will have to pay the publishers for those ad events and spend money in each source game. The amount of money a publisher or a target game spend in different source games is called the profile of the target game. Then this profile can be pretty useful to create embeddings. These embeddings could be used in many different places, like fraud detection, like revenue optimization, and other use cases. This is where the graph-based embedding approaches can play an important role in. So here we trying to create the graph-based embeddings via graph-based algorithms like node2vec and FastRP. And the results will be used in the subsequent ML tasks, concatenating with other embeddings as well. This all providing value to our later work. All right, thanks for watching. This is barely what I'm going to presenting today. And if you have more questions, just feel free to ask.